Lesson 47 is area under a curve, and this is like part 3 of area under a curve. Remember when we started, we would graph the function and we would have a certain number of triangles. So I would tell you how many rectangles, so I would tell you how many rectangles. And then we move to infinity, those really long problems. And today I'm going to give you a shortcut of area under the curve, and it's called the fundamental theorem of calculus. Okay, this is what we did before. Now don't copy this down because you already have examples like this in your notes. But to find the area under the curve, we graphed it, we found the delta x, we created this table, we came up with the equation. I didn't even finish because then we go to our formulas. So all of that is how we found the area under the curve before. And it took us a lot of work. And now what we're going to do is we are going to use the shortcut. So I have a function f of x equals x squared plus 5. I'm telling you on the interval of 1 to 3, I want to find the area under the function right here. So your first step is to graph this. So you are going to take and graph it. It's an x squared. It crosses here at 5. And we're going to go from 1 to 3. So this is what our function looks like. And what we're trying to do is find the area underneath the curve right here. So that first step is the same. But from here, we can now use the fundamental theorem of calculus. And that says all we have to do to find the area under a curve is to integrate. Integrate between these values. So in this case, we're going to integrate from 1 to 3, and we're going to put our function there. So x squared plus 5, and we got to put the parentheses in the dx. And all we have to do to this is integrate it and then evaluate it between 1 and 3. So in integrating this, I'm going to add 1 here and then divide. So I have 1/3 x to the third. And when I add 1 to x to the 0 power, of course, I just get x to the first. And I don't have to put the plus c, because instead what I'm going to do is I'm going to evaluate this between 1 and 3. And when you evaluate it, you don't have the plus c because we're going to get rid of that potential constant that's there. We're going to start with this value of 3, and we're going to plug that in for the x's. So what I now have is 1/3. I have 3 to the third plus 5 times 3. And once I've done that, I'm then going to take this second value, and I'm going to plug that into both of the x's, and I'm going to take and subtract them off. Now here's where you have to be really careful. You're subtracting this quantity. So it's 1/3 times x to the 1 to the third. So 1 to the third, of course, is just 1, plus 5 times 1. All of that is going to be subtracted. So I have a 1/3 plus a 5, or 5 and 1/3 right there. And I'm going to subtract off, let's see, this gives me 27, and 27 over 3 is 9. So I have 9 plus 15, so I have 4 minus 5 and 1/3, so that's going to give me 18 and 2/3. Or I could even write that as 56/3. And that is units squared, square units. So that is my shortcut. I can find the area underneath the curve here without going through all that work, just by integrating with respect to the two endpoints. The important part is you always start with this top number first, and then you subtract the bottom number second. All right, let's take a look at another example. It says find the area under the graph of this between 0 and pi. So again, first of all, we want to graph this. So we have to know what a sine graph looks like. And a sine graph starts at the midline at 0. And it increases before it decreases. It looks like this here. And this is 2 pi, and this is pi. So we want to find the area under the curve between 0 and pi. So this right here. So anytime we see area under the curve, we need to think integration. We are going to integrate from our endpoints of a to b, or in this case, 0 to pi. So we're going to integrate from 0 to pi, and we have sine of x dx. Do not forget the dx. Well, we know the derivative of sine is cosine, so if we go backwards, the integration of sine is going to be negative cosine of x. And instead of putting the plus c, we are going to evaluate this between 0 and pi. We start, remember, with the top number, pi. We're going to plug that in there. So we have negative cosine pi, and we're going to subtract off the bottom one. So negative negative and a cosine at 0. So at pi, that's sitting right here, that ordered pair is negative 1, 0, so the x value is negative 1. So we're going to take a negative negative 1. And at 0 right here, we have 1, 0. So here we have plus 1. And this is 1 plus 1, which is equal to 2. So the area under the curve is 2 square units. If you forget the square units on the back end, you are going to lose some points on the test. So always make sure you put units on this. And one more right here. And this problem is a lot more complicated. If we were to graph this, we'd need to plug it into our calculator and sketch a graph. I'd highly recommend that you do that because we're going to find area between two values later. So you should do that. Start with that. I'm not going to do that. But now, because we're looking for area under something, we know immediately we're going to integrate. So we're going to integrate from 1 to 2. And then we have 3e to the x plus 2 over x plus x squared times dx. Okay, so now let's integrate this. We know that e to the x, 3e to the x is just 3e to the x. When we're integrating this, remember, if we try to write this as x to the negative 1 power times 2, and you take and you add 1, you get a 0. And you can't divide by 0, so you know you made a mistake. So remember, this right here is just the natural log. So we have plus 2 natural log of x. And then we have right here, when we add 1, we get 3, and then we divide, so we have 1/3 x to the 3rd power. And instead of putting plus c, we're going to evaluate this from 2 to 1. We're going to start by taking that value of 2. We will plug in 2 for all of the x's right here. Once we do that, we will plug in our 1, and then we will subtract this. You can see I'm going to have a messy answer here, but it has to be an exact answer, so I'm going to continue to go with this. So when I plug in 2, I get 3e squared plus 2 natural log of 2 plus 1/3 and x, or 2 to the 3rd is 8, so actually I'm going to make that 8/3. So all of this, and then I'm going to subtract off 3e to the 1st power plus 2 natural log of 1 plus 1/3. And what I'm going to have right here is this is natural log of 1 is 0, so that's going to be a 0. So I have minus 3e minus 1/3, because remember I'm distributing that. And here I have 3e squared plus 2 natural log of 2. This is irrational, so I'm going to leave it. And then I have plus 8/3. And the only thing left that I can do is combine my constants right here. These are the only like terms that I have. And that will then give me my answer. And what I get there is 7/3. So this is my answer. And again, it has to be an exact answer. We always want an exact answer. So that is the only acceptable answer right there. Of course, the order wouldn't matter as long as you have the signs correct. Okay, 2 more problems, and these are just evaluating problems. So if I ask you to evaluate the integral from 0 to 4, and I give you a function, you already know how to do that. All you have to do is integrate the 8, which is 8x, integrate the negative 2x, which is when I add 1, I get 2, and then I divide, so it's going to be minus x squared, and just evaluate that from 0 to 4. So I have 32 minus 16 in the first one when I replace all those with 4s, and then I have minus 0, so this right here is just an answer of 16, and again have unit squared. And as I wrote the unit squared, I realized I forgot unit squared in the last one, but that was because my equation was so messy. Truly, it should still be there. All right, you can pause the video and try the last one really quick. And there you go. For that one, you should have 26 2/3 square units. Okay, really quick to summarize. We have talked about indefinite integrals, and we said with an indefinite integral, we put the plus c at the end. There are no endpoints right here. What we did today is also called the definite integral. The fundamental theorem of calculus says we do have endpoints right here. It allows us to find an area under the curve. So every time it says area under the curve, you know to integrate with respect to those endpoints. And you take the top value first. Once you integrate, you plug that in and you subtract off the bottom value. So a definite integral has a definite answer versus an indefinite integral does not, and that's why we put the plus c. Do not put a plus c on a definite integral or it will be wrong. Here's your assignment for lesson 47. You can submit it into Schoology when you're done. Have a good day. Bye.